Hello everyone, I'm Huanghuang Liang from Wuhan University, and today I will present our paper, Spirit, Decentralized Model, Aggregation for Scalable Federated Learning. I will introduce the background of this paper. Firstly, Google has proposed the federated learning to enable machine learning on edge devices, since edge devices are not owned by the FL coordinate, but can be federated instead. There can potentially be a huge number of edge devices, and the volume of data trained in each edge device becomes less. Secondly, the widely used machine learning framework is PS architecture, where model aggregation is employed after training on devices, which introduces communication loss, especially the delay caused by the model aggregation. Congestion can even be greater than that caused by model computation. Two problems on this slide. Existing models may suffer from problems below. Firstly, in PS architecture, computing is decentralized to edge devices, yet model aggregation is still executed by PS server. Deploying more devices can share compute tasks, while in some particular scenario, the total training time will increase due to model congestion. Secondly, gospel learning tries to solve the problem with a fully decentralized design. It only exchanges models with neighboring works. It will not introduce model aggregation congestion in each training iteration. Yet, when the number of workers increases, GL will be heavily affected by a lack of model synchronization due to its ad hoc nature, which leads to low accuracy in the training machine learning model. Thus, our goal is to shorten both the training and communication time as well as maintain the training quality on a larger scale. In this paper, we present the Spirit, a tiered architecture to decentralize the model aggregation. First, in Spirit, a cloud server acts as the FL coordinate and the edge device are organized into clusters. Selected edge device act as cluster heads, and the workloads of model aggregation are distributed to cluster heads, which mitigates communication congestion problem of PS. Spirit also regulates model aggregation with tied structures, thus guaranteeing high training quality which beats GL. Two challenges on this slide. With such a new architecture, two questions need to be answered. Spirit answered the first question with a new algorithm to cluster the edge devices with heterogeneous cavities, which an objective to minimize the model aggregation congestion. Spirit answers the second question by a runtime adaptive algorithm to regulate intra-cluster aggregation and inter-cluster aggregation. With those two key contributions, Spirit minimizes the model training time while monitor both the training quality and the model aggregation congestion. When a training request including machine learning model arrives at Spirit, the workflow is in 4 steps on this slide. The current FL system has no concept of clusters, and the cluster head. The training parameters, such as the aggregation interval, learning steps are fixed. Those and the associated algorithms will be extended by spread. Architecture on this slide in spread. Each work has a set of local data and a local model called the edge model. Each cluster head has a model called the cluster model. Training is an iterative process. In each iteration, workers use the optimization functions to update model based on the local data and the edge model. We adapt the parallel significance model (SSP), i.e. the difference between the local model and at any worker and the global model should be bounded. The key steps of our training process in spread are as follows. Key steps on this slide. The above steps repeat until the global model converges. The spread cluster construction problem (SCCP) in NP hard, which can be proved by transforming the problem into the minimum set cover problem. Thus, it's unrealistic to find a globally optimal solution within polynomial time. We explain the key modules on this picture. Text part shows the function of each key module. Spread employs a parameter controller at the server to adjust the intra or inter-cluster aggregation intervals according to the real-time training state. The parameter controller calculates the training state, runs an adaptive aggregation interval algorithm to compute the intra or inter-cluster aggregation intervals after each inter-cluster aggregation, and generates the federated learning plane. In this slide, we jointly analyze the runtime and the error convergence of spread. First, for runtime analyzing, the derivation of the total time to complete inter-cluster aggregation is given. Then, for joint analysis with error convergence, we combine the runtime analysis with error convergence analysis for spread. Training time and the training quality are two main metrics to evaluate a model training system. Fully signals SGD can achieve the highest training accuracy. Spread takes SGD as its structure. So the problem we face is how to minimize the model training time at the same time. The server sends the global model to the cluster heads and workers, waiting for the cluster head to retain the cluster loss. Then, the server recomputes the global loss based on the received cluster loss. Finally, it computes the intra or inter-cluster aggregation interval of each cluster. In this section, we prove the convergence of spread, show the lemmas and the theorem. Then, we implement a prototype of spread based on current FL system and the TensorFlow Federated. We implement the spread server on the Amazon cloud, and the cluster head and the worker on the Raspberry Pi 4 Model B. For spread server, explores the selector module in FL system. Server aggregator module inherits the master aggregator in FL server, and the additional function in SA is to collect the training state, i.e. the edge loss, the cluster loss, and the global loss pair aggregation. For cluster head, we implement the cluster aggregator module by extending the aggregator in the FL system. For the worker, explores the FL runtime and the example store modules in the worker or FL directly. For the IID case, we assign each worker images for 10 classes of the images in C file for 10 randomly. Thus, the dataset among workers is IID. Then, I will introduce the evolution of this paper. For picture A, we can see the decreasing speed of global loss of speed is significantly faster than that of FL and running or reduce. For picture B, we see that speed achieves in faster training computation time 1.17 days, 36.39% acceleration as compared to FL, 5.04 days, and 35.59% to running or reduce, 3.4 days. In picture 3, a faster convergence speed in terms of communication round means a better training quality of each interaction. For last picture, FL suffers the communication congestion. Ring audio suffers slow model synchronization. Finally, emphasize the key advantages in the middle. We use the FL score to evaluate the training accuracy. In picture A, speed outperforms FL and ring or reduced by around 5% and 10% respectively. This validates the measurement results that frequent aggregation can achieve a low function loss and a high training quality. In picture C, when the training system scales to 5,000 workers, the model training times of speed is 1.06 days, 8.04 times acceleration as compared to FL, 8.53 days, and 5.58 times to ring or reduce, 5.92 days. For picture D, when the scale of the system is small, the computing times dominates in FL, and as the scale becomes larger, the communication times dominates. Thus, that total modern training times still increasing. Finally, emphasize the key advantage in the middle. As shown in slide. In picture A, FL suffers a high heterogeneity degree compared with ring or reduce and speed. With speed, the struggle only influences the intra-cluster aggregation of its cluster. The scope of influence is smaller than that in FL. In picture B, speed can achieve an even better performance, especially the model training time when training on IID data. In picture C, speed outperforms performance fixed cluster size structures by 2.54 for 3.21 times. In conclusion, in this paper, we present spreads to decentralized model aggregation. Spread yields an 8.05 times and a 5.58 times model training speed up as compared to existing FL systems supported by the PS and or reduced architecture. Thanks.